Let's prove this identity by mathematical induction. We have here 1 plus 2 plus 3 plus dot 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 plus n. In short, the sum of consecutive integers is equal to n times the quantity n plus 1 all over 2 for all n greater than 1. Now, there are a lot of references with different explanations as to how mathematical induction is conducted, but specifically, it only has 3 different steps. And we're going to show the proof for this identity here. We start with the first step when in proving mathematical induction is we need to establish that this is an identity when n is equal to 1. Because if n is, when n is equal to 1, will not make this identity true, then there's no need for us to proceed with step 2 and step 3. So our left-hand side, when n is equal to 1, is this value here, which is 1. Okay? Now, for our right-hand side, we are given with an expression. Okay? We are just going to substitute n equal to 1 to that expression. And the reason why we started with 1, because that's the lowest bound or the smallest possible value for n here. Okay? In short, we are going to pick the smallest possible value for n. So we have 1 times 1 plus 1 over 2. This gives us 1 times 2 over 2. Then that would be cancelled out. Our right-hand side is equal to 1. Noticeably, the value for our left-hand side and our right-hand side are the same. So we can now say that we have satisfied our first condition. As mentioned, if this is not satisfied, there's no need for us to proceed to the second and the third steps. Now, our second step is when we assume that n is equal to k. In other words, we just simply use the variable k instead of n, because this will be used in a further verification using only the variable n. That would mean our identity now will become 1 plus 2 plus 3 plus dot 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 plus, instead of n, you will have k is equal to k times k plus 1 over 2. This is now the identity if n is equal to k. Before we go to the third step, there is a miscellaneous activity here for step 2 that we really need to emphasize. That is, since n here, or k in this case, is expected to be the largest possible integer that we could substitute in our identity, what if we consider another integer greater than n, or greater than k? If we have another integer greater than k, so we are going to look for an expression for our left-hand side and right-hand side where we expect k plus 1 as an integer larger than k. Of course, if we have 99, the integer larger than 99 is 100. If we have 23, the integer larger than 23 is 24. So specifically, you have k plus 1. What happens then is, if we're going to introduce that integer greater than k, our new left-hand side will be in this form: 1 plus 2 plus 3 plus dot 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 plus k, of course, and then plus, you will have your k plus 1 as you introduced an integer greater than k. Okay? Now, since this is an identity, or we expect this to be identity, once we add something on our left-hand side, we also add the same thing on our right-hand side. Take that our right-hand side here, expressed in k, is k times k plus 1 all over 2. Then we are going to add the same quantity, k plus 1, to ensure that we are not changing the identity as expected. Okay, now take note of this right-hand side, and this will be very important as we proceed to our third step. Again, the point of step 2 is when we assume that n is equal to k and introduce new integer greater than k, that's k plus 1. Take note this is k plus 1 because our definition here is just simply k. If it's expressed differently, then we are going to express this new or additional integer greater than that in that specific quantity as well, and we'll have that a separate video. Okay, again, take note of this, will be used on the third step. Now, our third step, as mentioned, we have here. Our first step is when we check the identity when n is equal to 1. Our second step is when we assume that n is equal to k. The third step is, let us try to assume that a is equal to k plus 1. On our given expression here, this is our given expression, specifically on our right hand side, it was actually n times n plus 1 over 2. Now, if we are going to have n k plus 1, this is in connection to what will happen, or well, what happened on our step 2 and what will happen next. We are going to substitute k plus 1 to our n here. In short, this is what will happen. Okay, sorry for that. This is equal to k. So what will happen? K plus 1. What will happen here is it will become, instead of n times n plus 1, you will have here, okay, take note of that, you will have k plus 1 as our n, times, you have k plus 1 plus 1, sorry, this should be bracket, all over 2. Because our original form, going back here, it was actually n times n plus 1. So this is our n and n plus 1. Okay, n and then n plus 1. Sorry for that. Let me go back to my original size. Okay, so now this is our right-hand side on our third step. If you would like to, you can also simplify this, making sure this will be combined. You have k plus 1 times k plus 2 all over 2. This is the right-hand side of our third step. No need to multiply this because the goal of mathematical induction is this. And this is where we go back to this equation here. The goal here is the right-hand side of our second step. We are going to manipulate it, and it should return to our right-hand side on our third step, as they both considers k plus 1 as our next integer of the identity. That's the goal here. That's why we already introduced this right-hand side earlier. And we're going to manipulate this right-hand side of the second step to reach this third step here. Okay? That's the goal of the third step. So, without further ado, let's try to come up with our simplified form of our second expression, second expression of our right-hand side. In our step 2, you will have k times the quantity k plus 1 all over 2, plus you have here k plus 1. Take note of that. This was the asterisk earlier. And we will be manipulating this to return to this expression. And if we can, then we have proven the identity using mathematical induction. If we cannot, then the given identity is not an identity. So how do we simplify this? Of course, you're going to introduce all mathematical and algebraic processes that you can imagine or think about, as long as you can make some changes or necessary combinations or simplified form of this. Of course, you could attack this by LCD, and then 2 divided by 2 is 1, so you will have the same numerator. But for your second expression, of course, this is over 1. 2 divided by 1 is 2 times that, so you will have times twice k plus 1. Because if you're going to treat with this is k plus 1, we return to the original form. Okay, from here, we don't need to multiply that. There are some instances that you need to multiply or distribute your coefficients here. But since our goal is to reach a result of k plus 1 times k plus 2, you already have your k plus 1 here. You simply factor that, and since it's both found on the on 2 terms, so what retains on our first term is simply just k. You will have plus this, what remains here, 2 all over 2. As you can see, just by that simple step, we arrived to a conclusion that the right-hand side, or the simplified form of the right-hand side or the second step, is just the same as the simplified form when we look into n equal to k plus 1 on our third step. Okay? They are just the same. This shows that our identity is really an identity under mathematical induction. This is how we, again, prove identities using mathematical induction. The first step is to show that it's true when n is equal to 1. Step 2, we assume that n is equal to k, and we'll have this expression. Then introduce a new integer greater than k, that's k plus 1, which will be added on both sides of the equation, taking a note of what happens to the right-hand side. As you go to the third step, you will now substitute k plus 1 on the n of our original identity, and we are going to manipulate our, going back to the right-hand side of our second step to arrive to an expression just equal or the same with the expression on our third step. Thank you very much for watching.